Hey everyone, this is Mayur. Welcome back to MLWorks. In this video, we'll try to understand what is mixture of agents and how it enhances the text generation from LLMs. And we'll also look at the basic code block for performing mixture of agents using a library called as Together. Okay, so let's get started. So in the previous videos, in one of the previous videos, right, I talked about MOE, which is mixture of experts, where you have multiple subnetworks in a single model, where each of the subnetworks try to understand the nuances of a data set. Okay, for instance, if you have a text data set, one subnetwork will understand the grammar, this other subnetwork will understand the noun phrases and similar other structures in your text. Okay, but in this case, okay, when it comes to mixture of agents, instead of having subnetworks, you have multiple models, large language models, and they take in a single prompt, all generate a different set of responses based on their understanding. And then you have a final aggregator model, okay, which tries to refine the results which are generated from all the other models. Okay, so that's the idea behind mixture of agents. So it is a layered architecture. Okay, so consider you have, right, four LLMs. Okay, and you have a single prompt that you are passing to the your LLM, and each LLM will generate their responses. Okay, the final LLM will try to understand the responses from all the previous LLMs and synthesize based on the prompt that you give, okay, to the aggregator LLM. Okay, it will try to synthesize a response from the all the LLMs that was generated, the response generated from the previous LLMs, and it will give you the final output. Okay, so it will, in general, right, it results in better understanding of natural language and also the text generation that happens based on the kind of input you give. So the key idea is to generate better responses by referencing the output from the other models. Okay, and if you see here on the right hand side, okay, you have a single prompt and which is passed to and layer 1, which is again containing a multiple agents, which could be multiple LLM models. And then there is another layer L2, okay, which is again a bunch of LLMs. And if you see, there is the same input could be passed to the next layer as well. Okay, so there is dependency between kind of previous layer and also to the initial prompt as well. Okay, and at the end, if you see, there is a final output, and it is also again another LLM, okay, which synthesizes the output based on the responses that it generated from the other LLM model that's generated. Okay, so for instance, layer 1 generates a response independently. Layer 2 agents refines these responses using output from layer 1, and layer 3 further refinement continues through the additional layers. Okay, the final layer aggregates and synthesizes the responses from the other model, which is layer 1, layer 2, layer 3, and generates a single high quality output. Okay, so the general architecture of mixture of agents is based on the number of layers you have and the number of agents per layer you have. Okay, that is the general architecture of mixture of agents. So why it is better, right? Because consider, right, if you have a single LLM, okay, generally it will be what the training an LLM is quite challenging because it requires large amount of training data. The model size is also huge, and the compute requirement is also quite expensive to manage. Okay, so but you can manage or you can build a mixture of agents kind of a setup where you have multiple open source models, okay, which are good at specific tasks, okay, which excel at various tasks, and you can manage those LLMs independently, okay, and based on the kind of tasks you give them, the responses will be better by combining the responses from the multiple models. Okay, and that's the basic key idea behind MOA, because it helps you to beat the large language model, the state of the art models, by combining the results from the multiple LLMs. This is kind of like a ensemble of LLMs. Okay, so what it resulted in? Okay, so when you compare the results from MOA against other large language models, okay, on various specific benchmark data sets, okay, so if you see Alpaca Eval 2.0, so it achieved a 65.1%, okay, outperforming GPT-4o, okay, which results in 57.5%. and there is empty bench. It will give the top position even with the marginal improvement over already high performing model. And that is on the Flask data set, there was substantial improvements in terms of robustness, correctness, efficiency, and factuality, common sense, and insightfulness. So overall, when you try to combine multiple models, okay, the models tend to provide better results, okay, irrespective of how the input you give, okay, if even if the initial output generated by the LLM is poor, over the next set of iterations or layers, okay, the output gets improved, okay. And here, if you see on the right hand side, there is this bar graph. Okay, when you compare against the single model with the response from the other models, okay, for all the different data sets, in this case, it is Alpaca Eval 2.2. Okay, all these models, Qwen 1.572 billion, 110 billion, and then Wizard 8. Okay, then Minstrel, Llama 3. Okay, all these models gets outperformed by the architecture, MOA architecture, because it combines the responses from multiple models. So overall, when it comes to what the performance time, okay, the accuracy or performance, this is quite better when compared against single individual model. Now let's understand how we can implement mixture of agents through Together library. Okay, so I won't be running this model or code base here. We'll just understand the code here because it requires us to generate an API key, and when you try to use that API key, it is always like rate limited because it has to generate a lot of response. The token size is high. Okay, so it is not able to generate the response. So the code base is quite simple. Okay, first you just have to do pip install of Together, and then you can generate the API key from here. I better won't suggest to do this because even if you generate it and try to apply it, okay, it won't be sufficient for generating the response. You need somewhat paid account, then only you can generate what response for using all these four models, and then you can get the results. So yeah, first thing is you have to install the package, then you have to generate your API key. Okay, so in this example, what they do is they have two layers and four LLMs. Okay, and there will be a final LLM, which is the aggregator LLM. Okay, and here if you see, let me just go to the code itself. So what they do is initially they import async IO, and there is import OS, and from Together they import two functions, async together and together. Together is nothing but your client, and async together is again a asynchronous client that is getting created. And this is the user prompt, which is what are the some fun things to do in San Francisco, which is SF. Okay, and then there are reference models. So these are your models in or agents or models in your layers. Okay, we are using Qwen 2 72 billion, and then Llama 3.3, and then Minstrel and Databricks Instruct. So we are using these reference models, and there is a final aggregator model and final aggregator system prompt. Okay, so final aggregator model is again Minstrel 8 72 billion parameter, and in the prompt what we give is we have been provided the set of responses from various open source models, okay, to the latest query, and your task is to use these responses turn this into single high quality response. It is crucial to evaluate the information provided in these responses, recognizing some of the if I go back, some of its bias or incorrect. Okay, so we are mentioning everything here. Okay, when it comes to the prompt, we are mentioning that you will be getting a responses from the four large language models, and you have to find the best response by combining all these four responses, irrespective of it may be even incorrect or biased output from one of the LLMs in the previous large language model. Okay, you have to understand that, and you have to generate the final response. Okay, and then what they do is they write a function called as run LLM. Okay, here they give the model, and there is the user prompt, which is this one. What are some fun things to do in San Francisco? And there is this temperature and max token, and then you get the response. So this is where you will be passing your reference models and generating the response. So if you see here results in another function, async function, you are iterating through the reference models and passing it to the run LLM, which will be happening simultaneously. These calls will be happening simultaneously. Okay, So for each model, okay, Qwen 2 72 billion, this will be the input. For Llama 3.3, this will be the input. Okay, it will be generating the response for each, and it will be getting stored in results. And what we do at the end is, okay, we use something called as client.chat.completion.create. Okay, and use the aggregator model, which is Minstrel 822B. And then we pass our system prompt, which we have here, which will contain the instruction like you have to take the response from 4 models and then have to generate a single high quality response. That is your system prompt for this one. And then the response that we got from here, results, okay, will be added here as part of content, as a user content. Okay, so this will be passed here, and we'll be generating our final response. Okay, and this is how we'll be generating your final response. That's choices of 0.delta.content. Okay, so this is one way of implementing mixture of agents. Okay, this is where you have one layer and multiple LLMs inside it. So this could be what become can be made more complex, where you have multiple layers and multiple what LLMs. In this case, it was only one layer. Okay, I guess it is only one layer or 2 layers, if I'm not sure. Here, okay, here it uses 2 layers also. So this is example for one layer, I guess, because we just have one layer here. But there are also possibility where you have 2 layers, and there are like 4 models again under each layer. So if we go and look at this specific example, okay, again we are like setting up the client, async client and client, and then user prompt and the reference models, aggregator model and aggregator system prompt. So here we are mentioning layers is equal to 3. Okay, and then if you see here, and in sleep time 1 2 3 1 2 4. Okay, and if you see here, so this is aggregator system prompt and the previous response. Okay, so what we do here is, if you see, so there is reference models, the results are generated, and then those results are again passed to another model, that is again they are passed to the LLM, and it is taking the results from the previous layer. Okay, and then again generating the response. Okay, and finally it is getting sent to the system prompt, and then it is generating the final response. So this is the code for this specific architecture, I guess. Okay, so this is one way of what improving the performance of your large language model. Okay, and with that I'll be concluding this video, and I hope you learned something in this video. Thank you for watching.